Okay, I know this is the last talk of the day, so I'll try to keep this brief. This is a project that was a combination of old and new, and it was interesting what work they did
Sorry.
here.
Sorry
Sorry.
to interrupt you. I forgot to share the screen, so no one on Zoom can see your. Fantastic
Okay, well, I didn't
presentation.
really show anything exciting. They just missed the title slide. But this is my colleague, this was work that was done by my colleague, Paul Wood at Southwest Research Institute, and Alex Berry, who's with Aurora Engineering. So I'm going to talk a little bit about the problem that they were trying to solve, the technical approach that they took. I'll talk about the software that was used here. It's called the Module for Event-Driven Operations on Spacecraft, MEDOS. And then how we went about building a test bed for MEDOS, and then I'll have some conclusions. The motivation behind this was to mature the state of the MEDOS software. MEDOS software is a new development from Aurora Technology, and NASA has the concept of technology readiness levels. And often when you're writing a proposal, you'll want to be able to show you have reached TRL level 6, which is in our case a prototype demonstration in a relevant environment. There's also TRL 7, which means you've actually got a system prototype in the space environment. So this project here, we're shooting for TRL level 6, and with the setup that we have, with a later plan to go to try to get to TRL 7. And so that was the motivation behind this. So the prototype in this case is the MEDOS software. Again, that's the module for event-driven operations of spacecraft. And we identified a demonstration mission. The demonstration mission was magnetospheric multiscale, which is an older mission. It's a big mission. And in order to go ahead and do this work, we had to get permission from the relative stakeholders in this project. Aurora Engineering, who was the creator of the MEDOS software. We had to contact NASA and Mission Management to get permission to do this. And we also worked with the Payload Operations Center, which is being operated out of the Laboratory for Atmospheric and Space Physics in Colorado. And then Southwest Research was involved. We developed the host software where we were going to apply MEDOS. And this test was using the FEEPS instrument. FEEPS is the Fly's Eye Energetic Particles Spectrometer. It's an instrument on the MMS spacecraft. And this was supported through, Aurora has a STTR project and through the continuing MMS operations. So I'd like to talk a little bit about magnetospheric multiscale, the mission that this was used as a test bench for this project. This was initially a NASA Goddard mission. It's a 4 spacecraft constellation. These are rather large spacecraft. If you were at the dinner or the lunch yesterday, these spacecraft are round, but they're about the size of the tables that we had at dinner yesterday. It launched back in 2015. So now we're getting into the 10th year of the project, and it's been going on very successful. 4 identical satellites, and there's a large, with a spacecraft this big, there's a large number of instruments. And the instrumentation on board are plasma and fields instruments, mostly for studying the goal of the project is to understand magnetic reconnection. So it has a very a broad goal. but the orbit passes through the magnetosphere, it passes through the solar wind, and it also passes through the Earth's radiation belts. So now that I've introduced MMS, I'd like to talk a little bit about the MEDO software, which again, it stands for Module for Event-Driven Operations on Spacecraft. And this is a framework that Aurora Engineering created to do onboard decision making. The concept was we want to do some automation on board. Now that we've been in operations for 10 years on MMS, a lot of analysis has been done of the data on the ground, and there's a lot of things that we understand now that we didn't understand then that would allow us to make decisions about which data on board to keep. Now, this is important for MMS because MMS can take gigabytes of data per day, but we can only download a few megabytes with each pass. So preserving the scientifically interesting data is particularly important. So having the automation on board makes sense. This is a case where the recorder really isn't the limitation. The limitation is the downlink. So using this MEDO software, we detect events from telemetry, and we calculate, the MEDO software does some calculations, and it creates derived parameters from the telemetry. And then from those derived parameters, it actually uses fuzzy sets to make decisions based on the values of the derived parameters. From its decision-making process, it produces a confidence that the event has actually occurred, and it can be used to trigger responses. It can be used to trigger onboard responses, say to the spacecraft, or to trigger responses on the ground. So I have a drawing here, or actually not a drawing, a figure. This shows different views and how MEDOS breaks down the views of the data. The top level, the very top here, I can show with the pointer. Whoa, we'll get it. Ah. Hope anybody can see though. Well, we can just start with the top and move down. I don't want to distract you too much there. But with the top, there's a pitch angle distribution showing the relative intensity of flux to the magnetic field direction. And then the MEDO software derives from that a deviation showing the field strength relative to the running mean. And then the third plot shows a derived counter-streaming ratio that shows the strength of the parallel and the anti-parallel flux. And then the final plot or strip along the bottom shows the relative scores that show the confidence that these are micro-injection events. And by micro-injection events, we mean bursts of electrons. So that's what MEDOS is looking for in this case. So MEDOS has several triggering conditions for crossing the magnetopause, crossing the bow shock, and entrance into the outer radiation belt. The data is from, again, I mentioned the fly's eye energetic particle spectrometer. It was used in this demonstration, and it provides the scientific information that's used for MEDOS to trigger. This is another set of plots. This shows a simulation, well, it's actually real data from MMS that was from when we transfer through when we transition through the radiation belt. And there's really two sets of scores here produced by Meadows, a conservative set of scores and a risk tolerant set of scores. There's just a little bit wider band on the conservative scoring than on the risk tolerance scoring. So the next thing I'm going to talk about is the demonstration that was put together to validate the Meadows software for TRL level 6. And again, it uses the FEEPS instrument, which I mentioned. Another important component that I didn't mention is the central instrument data processor. This is a payload processor which receives the data from the instruments. In this case, it receives the FEEPS data, and it also does calculations for FEEPS. FEEPS is a very simple instrument that runs, just runs off of an FPGA. It produces data, and the processing is actually done on board the central instrument data processor. That produces the trigger data, which is what we're looking to do in this case with Meadows. That could trigger action on the spacecraft processor, which is a separate processor from the CIDP. And that could be done through the watch point, action point mechanisms that are already built into the flight software there. This talks about the SITIP. Again, the SITIP does the processing for FEEPS. I mentioned that. There's a special task running within the SITIP flight software, which does the data processing for FEEPS. There's 2 FEEPS on board, so that task will actually process data for both instruments. When no data is coming in from FEEPS, the task is basically sleeps and doesn't do any work. So what we're looking to do here with Meadows is label the data, which is in the CIDP, that's trigger data, and the CDQ stands for data quality, or so we're marking the data with certain data quality, and that data gets downlinked first. So that's how the triggering the trigger gets computed to a data quality. The data quality marks the data, then the marked data gets downloaded. So going into just the patching process, we we turn off the FEEPS and then upload a patch, and then activate the patch, and then turn the FEEPS back on. So this stops the flow of data so that the onboard task processing isn't actually executing or trying to process data that's coming in while we're applying the patch. So those steps are just outlined here. Applying the patch, and then we can actually run a test after we've applied the patch. This shows a bit more detail in terms of how the patching works with the older system. The way the flight software was compiled on the central instrument data processor, there's a code segment, and then there's the initialized data segment. I don't show the BSS segment in this diagram, but there's actually a gap in the way we've compiled it, because the data segment has an aligned buffer in it that leaves a little bit of unused memory between the code segment and the data segment. Originally, actually, for operations, the FEEPS instrument was patched before we got into using Meadows for this demonstration. It was patched because the FEEPS instrument itself, during the launch, there were thin foils, some of the thin foils on the eyes were damaged. And so we applied a patch later to the software, which modified the survey data so that that we can take out where some summation is occurring. We can take out the errors that have to do with those eyes that have the damage. And so this shows the unpatched software. We apply the patch actually in this area between the code and the data segment. And that's the way MMS had been running in normal operations. So for Meadows, we've decided to alter the patch and make the patch bigger. It actually turns out that with the select part of the Meadows software that we needed to do analysis of FEEPs, the patch will fit within that section. So we were able to put the patch for the survey data and now a patch for the trigger data, which is the Meadows patch within that same piece of memory. This is just the process for reverting the patch. We, after inserting Meadows and doing our testing with Meadows, then we can go ahead and remove the baseline patch and go back to the patching just for the survey data. And then this last part here just shows our test bench. This is what we did is we used the flat sat that we have for maintaining operations and testing operation scripts. And we added a new simulator to it. And that simulator replays some pre-recorded FEEPS data and sends it through, it's actually just a UART interface to the central instrument data processor. And then by flowing that simulated data, then we're able to actually test Meadows with live data. So that was our setup for that. And I think that's it. I just have some references for the Meadows software itself and various other parts that are mentioned in this presentation.
All right, thank you, Robert. Questions? Having worked flight dynamics for MMS, I just want to know who you're calling old.
One question.
So the MMS, is this the one that runs on the cold fire that's like really like?
No, it runs on a Leon, but it does run RTEMs.
Okay, I just remember there was one. I was just remembering. The Leon is probably more powerful than what I remember the cold fire, because the cold fire was pretty weak. So
Right.
did this put much burden on the processor?
No, no, it didn't. And the patching method that we came up with, actually, we came up with it with the idea of RTEMs in mind, because we had previously used VxWorks where we have a dynamic loader, and I think that's a capability now with the newer RTEMs. For the RTEMs that we used at the time, what we were able to do is create subroutines, create just selective subroutines to replace, in the case of the survey data or in the case of the trigger data, replace those individual subroutines and then use a static linker map and identify the dependencies. And then that would, we could load it into memory, insert 2 branch instructions, and then we've just patched around the 2 subroutines that we needed to. The subroutine for the trigger data, we added the initialization to Meadows so that the first time it got called, it would initialize Meadows and then it would run. It was amazing to us that it was able to run, and the logic is simple enough. I mean, it may be considered a simple form of AI in that it didn't affect our performance to where we can run at the same cadence and the same rate and still trigger on these events.
All right, we have another question in the middle.
It's kind of related to this, but Was the area used for the patch, like actually, there by design, or it was like luck?
Well, it was somewhat luck. It makes sense. We have a buffer, a big upload buffer, and we had a statement in our code that says align this buffer. And it aligned the buffer, and of course, it left a big amount of space after the code segment ended, to where we found, okay, there's a lot of unused space here. We did have a lot of margin on RAM, so it wasn't the fact that it shifted didn't make that much of a difference. It would be a bit more complicated had we not had that area, because then we would have to worry about the heap space, because the area there's the code, data, BSS, and then the rest of the space was allocated to the heap. Since we had this nice block, we were able to patch there and not have to worry about disrupting the heap or messing up those data structures.
All right, let's give another round of applause for Robert and